Hi, thank you so much for joining us this morning, this afternoon, depending on your time zone. Today's session is co-sponsored by Pinfa North America and SAMPE, and the topic is meeting fire, smoke, and toxicity requirements for transportation composites. I'm the Vice Chair of Pinfa North America. I'm Maggie Bauman. And now I'd like to introduce Tim Riley, who is the Chair of Pinfa North America, and he will make some opening remarks. Tim?
Thank you, Maggie. Okay, I think everybody can see my slide. Okay.
Looks great.
Hello, ladies and gentlemen. Pinfa North America is delighted to have you attend this session on flame retardant composites for transportation. Our relationship with SAMPE goes back to 2013, when SAMPE Tech Director, Scott Beckwith, helped us organize a conference in Seattle on aviation fire safety. And we had a great success. We had about 100 stakeholders come to that particular conference. And our great relationship continues with SAMPE to this day. Okay, let's see if we can get the slide to go. Okay, Brianna?
Yes.
For some reason
Try to hit your mouse or the right key.
Okay.
There we go. A
We
little
go
too
back
fast there.
one. Okay, so something happened. Okay, so fire retardant materials are very important in the protection of life. Composites play a big role. If you look at worldwide, there is billions of people get on a passenger train every year, and they also use subways. About 25 million lucky passengers get to go on a cruise ship, and 4.5 billion passengers during the year 2019 flew with the global airlines. And as we know, the FAA has spent decades on research in order to improve the survivability of an in-crash, in-flight, or post-crash fire event. And this has yielded big benefits for the public. And this webinar today, we have companies such as Boeing, Safran Cabin, Southwest Research, UL. We have resin producers on the line today, Formulators, flame retardant producers, and these folks have all helped for this success story. You might ask, who is Pinfa? Okay, our member companies are flame retardant producers, they're resin producers, they're formulator of resins, and they're also plastic compounders, and the related professionals to this area. We strive for high global fire safety standards. We work to continuously improve our products concerning environmental health and safety profile of our non-halogen flame retardant products. And as part of our mission, we collaborate. We collaborate with industry, academia, NGOs, government, and other stakeholders. Pinfa is headquartered in Europe, but we also have affiliates in North America and Asia. Okay, since you're participating today, I think there's 150 people on the line. Many of you have interest in FR materials. Let Pinfa be a resource for you. We have a great free monthly newsletter, and it's been published now for over 10 years. It's monthly, and a lot of good information on what's going on, regulatory, new FR products, new resins, so on and so forth. Check it out, sign up for that. Here's the link, and we're going to make these slides available later. Application brochures. We have 3 terrific brochures on the electrical, electronics, building and construction, and transportation. please download those. They're about 50 pages each. If you want to know about 65 commercial non-halogen flame retardants and their application area, you can check out our product selector on the website. We do industry workshops, seminars such as today, webinars. Pinfa Europe just did one on e-mobility, and it had to do with fire safety and e-mobility, and they had about 200 attendees at that conference, including OEMs and so forth. It was very good. We're going to be doing something new on June 1st. We're going to do our first non-halogen flame retardant formulators training, and it's going to be 4 weeks. It's going to be about 2.5 hours each session over 4 sessions. Initially, we're going to focus on FR thermoplastics and elastomers, but we will have information on thermosets. But we hope at a future time, working with SAMPE, that we could also tailor a course just through SAMPE. We're going to talk more about that. Pinfa North America also, we do sponsorship of events, we do outreach. If you happen to be in October in Dallas at CAMEX, please stop by the Pinfa booth and say hello. Finally, I want to thank SAMPE for helping us put this on today, specifically Brianna, Raj, and Scott. And I also want to give a shout out to the great speakers we have today from world-class organizations. I think we're going to have a great webinar today, and I'm really pleased all of you could join us. Thank you. Back to you, Maggie.
Okay. I'll put my video back on. Okay. Now I'd like to introduce Raj Manchanda. Do I have that right, Manchanda? And he's going to, obviously he's with SAMPE, and he's going to shed some light on SAMPE's role in this composites area.
Hey, Raj, we can't hear you.
Thank you,
There you
folks.
are.
Again, it's been a great collaboration for all these years. As Tim mentioned, you know, it goes back to Dr. Beckwith and Seattle. My gosh, 2013, not too long ago, but it seems like eons away, you know, in this new virtual world that we live in. So I'm going to try to break up that monotony. And if you folks don't mind, as Tim mentioned, we have over 100, maybe 150 stakeholders from around the world. I noticed South Korea, US, UK, Japan, Bulgaria, Spain, France, Germany. So if you don't mind, in the chat, just say hello. Just say a quick hello, who you are, where you're coming from, and your location in the world, just so we can add a little dimension to this virtual world. But as Tim mentioned, my name is Raj Manchanda. I'm the Chief Technology Officer at SAMPE. SAMPE is the Society for the Advancement for Material and Process Engineering. Tim also mentioned, you know, a lot of the innovations happening in the transportation sector. For SAMPE, obviously, that is a very important group. Aerospace is really important. And the whole, you know, flame retardant, non-halogenated global community, not only the end users, but the manufacturers and the fabricators, we're really happy to collaborate with you guys, because I think SAMPE and Pinfa have a lot of touch points and cross points. A lot of the innovations happening, you know, in our colleagues, in our companies, Hexcel, Toray, others. I think this is what we're going to hear about today from UL, from FAA, from Boeing, from Airbus. So it's really an exciting time. I think technology is driving this, and we're really grateful you folks taking time out of your day to join us. It's going to be really captivating 3-4 hours of knowledge. You're going to be grateful for some of the talks that you're going to hear. Some of the presenters we have are world class. And Tim, I hope we continue this dialogue. I mean, I think this is just the beginning. Wait till October in person. We're all going to be safe. We'll have masks or no masks, whatever your preference is, socially distant. But I think life has to start to come back. So thank you, Tim, again, and Maggie, and looking forward to that in-person time.
Thank you.
Maggie, you're on mute.
Sorry, I'm trying to be. We have a couple of minutes and you want us to stay on time. So maybe a little bit more about some of the things SAMPE has planned over the next few months, Raj.
Oh, thank you so much, Maggie. I mean, my gosh, I didn't even have to pay you for that. So not only as Tim mentioned, our significant gathering CAMEX is an outlet. Tim, actually, for you to share all the outlets that PINFA has, I made some notes. And I know we're going to get the slides after, but those monthly newsletters are very informative. I did want to share that we are launching a new program called Materials Innovation and Advanced Technology Leadership Forum for next January. So that's in January in Huntington Beach, California, in the backyard of our friends of Boeing out there. But our focus there, and I think it might even come across in today's meeting, our focus is going to be how do we bring in the lessons learned from automotive? How do we do that and learn from that? Composites technology, materials technology. We all know that, production rates, in order to be viable for aerospace, they're going to change. We're not going to be able to make 100 units a year. I love the 787 or whatever the numbers are. We're going to need thousands of units. So if urban air mobility, vertical lift starts to take off, the fire retardant community, we're going to need their help. And we're also going to need lessons learned from automotive, wind, even Medtronic. We're talking to some folks in the medical device world. What can we learn from that side? So that's one message I have for this audience. Feel free to join PINFA, feel free to join SAMPE and contribute what you know. That I think for us is going to be very valuable, Maggie.
Well, thank you. All right. So I think first I would like to thank the speakers because they both were very, very good about staying available for us. We actually started planning this program over a year ago.
Right.
It was scheduled and rescheduled twice. And this group of speakers have hung in there with me. And I really, really, really want to say thank you to all of them.
Great. That's great. Hey, Maggie, from those of us who don't know much about PINFA, where are you guys headquartered in North America? And I know Tim mentioned Europe. So can you share a little bit about the global nature of the organization?
Yeah. Well, let's start with PINFA North America. We're kind of virtual, although let's call it our bank account and our executive assistant is in New Jersey. I'm also in New Jersey, but our members are wherever they're located. But we meet virtually and we try to get together in person. Hopefully, we will some point this year. But we've even had our board meetings virtually, and so everything's been continuing. PINFA started in Europe. It's located in Brussels. But again, the member companies are from all over Europe. And
you mentioned sorry, Meg, you mentioned member companies. So is it similar model to SAMPE? SAMPE has individual members.
No, we're a not-for-profit trade group. So our members are companies.
Excellent.
They're either FR manufacturers, that's Clarion and FRX are examples of that, or they are synergist producers. Those are the additives that help improve the efficiency of the flame retardant, the primary flame retardant, and then compounders, formulators, and even in some cases, end users.
Excellent.
Organization.
I think we're about on time now, Maggie. We hit the half hour.
Okay. So our first speaker today is a very, very experienced gentleman from the US FAA, Jeff Gardlin, and he's going to speak on cabin fire safety and innovation and research. He has served as an aerospace engineer at the FAA for more than 35 years with a focus on survivability and security issues. He's earned international recognition by developing numerous regulatory standards, guidance documents, and research plans to enhance safety and improve occupant survivability. He has conducted training in these areas around the world for other regulatory authorities and the aviation industry. In addition, he has been involved in the type certification of more than a dozen transport category airplanes. Jeff, would you kindly present? Thank you.
Maggie, let me share my screen. Before I do that. I will say, by way of introduction and full disclosure, if you attended the most recent FAA-sponsored International Fire and Cabin Safety Research Conference, and some of this may seem familiar, or it may not if at the time it wasn't all that interesting. But I did base this on a presentation made at that conference that Maggie attended and saw and asked if I could kind of adapt it to this audience. So that's what we're talking about here. So yeah, my focus is really going to be on for aircraft cabin and cabin fire safety and how innovation affects what we do in terms of research. Just an overview. What are the safety needs? What is it that we're actually trying to achieve? How do we approach that from a regulatory standpoint? What innovative technologies or applications might do in terms of how we approach this, and then just a little bit on some upcoming challenges. So let me just set a high level. For the most part, we have, and this was mentioned actually by Tim, that we have more or less two big picture objectives that we try to address from a fire safety standpoint. In-flight fire, which is kind of an accident prevention issue. In other words, if you can mitigate the effects of an in-flight fire, you can prevent an accident from occurring, which involves both the protection of the occupants as well as the protection of the airplane, because the airplane at that point becomes a necessary safety feature so that the outcome is acceptable. And then the other aspect that we look at is a post-crash fire. So now we're kind of assuming that there is an accident, and at that point it's a mitigation strategy. And really, at that point, the airplane is not really all that critical, except insofar as it allows the people survivability. So if the airplane is at the end of the day destroyed, that's okay, as long as the people are able to survive the accident. And this then plays into other mitigations in terms of things like impact protection and the ability to rapidly evacuate an airplane. So just looking at some contrasts here in fire threat. So the picture on the right is the result of an in-flight fire, and the picture on the left is the result of a post-crash fire. And if you look at the general condition of both airplanes, other than the fact that one is still on its gear and the other one is not, you know, they look pretty similar. But by way of contrast, this accident, there were no survivors, and in this accident, there were actually 100% survivors. So the end state may look pretty similar, but the outcomes can be very different. Now, I will say that the picture on the left is about 40 years old, and the picture on the right is about a little more than 10 years old, 15 years old maybe. So there is a difference there, and obviously standards have improved, but nonetheless, it illustrates that the situations we're trying to address kind of merge together. So we looked at multiple aspects of fire safety for the perspective of how does it provide benefit. You know, the first thing is to minimize the involvement of the materials. And so if you can keep them from being involved at all, obviously that would be, you know, the best objective, but in the real world, that may not be practical. So, you know, in that case, what we really want to do then is prevent the spreading of a fire. So from a propagation standpoint, to keep materials, at least try to confine what happens. And then from a post-crash fire standpoint, and even to some extent, if we look at an in-flight cargo fire, you're trying to prevent fire penetration. So keep the fire in whatever, keep it either out of the vessel, which is the entire aircraft, or keep it within the vessel, which could be a cargo compartment. So from a regulatory standpoint, there's different ways of approaching that. If you look at the current large airplane, transport airplane standards for the fire properties of materials, they're fairly specific. So they have requirements to meet this certain specification or perform this certain test in this certain way. And that's, as long as you know exactly what you're going to be dealing with, and you can kind of predict that as how things are going to be, then that's not a bad way to go, because you can be pretty sure that things will be done the way you want them to be done. But in reality, that may not be how things are. And so there's a benefit. I don't know if that phone is audible in the background, I apologize. But there's a benefit to having a more performance-based standard, which is to kind of define, well, what is the threat that we want to resist or mitigate? And we want to provide protection that's sufficient to enable, for example, time for people to evacuate. And then if we're really, adventurous, you can go to a highly performance-based standard, which just basically said, something like, we'll just, make everything safe. And then the mechanism by which you decide things are safe is defined in some non-regulatory way. But that carries with it other issues and challenges in terms of how to standardize and how to assure that people are in fact doing the diligence that you're after. So, how does innovation really impact that? And it's really, there's two sides to it. Obviously, a lot of innovation improves safety, and is in general just goodness. But the other side of that is that typically it means that the current standards, even if they're performance-based, the means of showing that you're satisfying the standard needs to be revisited. And in some cases, depending upon just how innovative something is, that can also be a pretty big challenge. There's something that was just, it's called the diffusion of innovation curve. It was a professor, Everett Foster, that developed this. And essentially what it's trying to show is that innovation is a challenge to integrate into any given practice. And so, this is showing that the bulk of the people don't actually adopt an innovation until late. And it's only a small percentage of people that actually sees some innovation in terms of applying it in whatever the form is. So from a standpoint of how the research fits in, the typical process has kind of been that there's research on whatever the new innovative product is. The product gets developed based on that, and then there's additional work that needs to be done, and it may involve further research to develop the safety standards that are required to accommodate that. And that's not necessarily ideal, because the typical scenario is that the product is done by that time, and you're really trying to play catch up in developing the standards. So ideally, we would be doing this sort of parallel process where the standards research is taking place along with the product research, and then to the extent that that's necessary, there can be a little feedback into that product research to help accommodate the standards that are needed. And I think in more recent times, we've had better success doing this than maybe historically. So it is it's something that we recognize. It helps a lot if we can follow that sort of path. So from our perspective, the ultimate goal is to produce the right safety standards, the right standards. And so basically we identify a need. The need can be from different sources. I'll touch on that in a second. We measure what the performance is that's important. And then from that, figure out, what the standard ought to look like using that knowledge, validate the standard, and then ultimately implement it so that it can be used and the, you know, the innovative product can be taken advantage of. So this leads to some interesting choices in terms of whether the research that gets done at that point is to meet the requirement, which is to say, you know, produce something that satisfies this specific standard, or whether it's done to meet the objective of the requirement. And sometimes those two are the same thing, but sometimes they might not be. So my examples there are kind of specific, and maybe for some in the audience may resonate just a little bit. But it is a little bit different, and it can be different. So some of the technologies that we're looking at that may involve changes to how we look at fire safety, additive manufacturing is an interesting one. I'm going to just touch on that in a minute. But other things that maybe don't have quite as an obvious connection, like supersonic transports or electric propulsion, hybrid electric propulsion, and then the concept of urban air mobility, those all may influence how we look at what's necessary for fire safety in the future. This chart, I put the big notional watermark on it because it's really, that's all it is, it's notional. But what we've sort of seen is that if you could measure the inherent fire resistance of a given material, and then figure out how many of the parameters that are possible variables in additive manufacturing are important, you see something like this, where, you know, the more fire resistant it is, the fewer things you need to worry about. But the less fire resistant it is, then there may need to be that many more controls over how it's processed. Now, this is, like I said, very notional, very crude at this point in time, but it does seem that it could get really complicated if, let's say, modestly fire resistant parts are made using additive manufacturing. I won't spend a lot of time on this because I don't have a lot of time, but and I'm kind of fascinated by this whole process of triply periodic minimal surfaces, which it's a mathematical entity that's been known for a long time, but advent of computing and the advent of the ability to produce things through additive manufacturing makes them much more viable as a practical application in the structure. And so what could you use them for? Well, it would seem that these things would have potential applicability for using heat transfer, dissipation, or potentially energy absorption, because you're getting a lot of surface area for a minimum amount of material. And so this may be something that, again, depending upon how the technology is applied, it could be interesting. I mean, you know, depending upon the requirement, I'm not really sure what the coupon should look like for something like that. New power sources. So, you know, we currently base what we think about post-crash fire protection on aviation fuel. But if we don't have aviation fuel, if we have electrical propulsion that's mainly driven by batteries, or, for example, fuel cells, then, you know, that might change pretty dramatically how we look at what is a post-crash fire and what is important in that case. So it's the kind of thing that we may have to revisit some of the other requirements to accommodate what we now understand to be the new post-crash condition that maybe we didn't see before. In reality, you know, technology is, generally speaking, moving a lot faster than the pace that we can adopt regulations at. We can use something called special conditions, which are a regulatory tool, and they're specific to a given program. It's not ideal, but sometimes we have to do it. But generally speaking, you know, the criteria are going to lag the design, and that's a challenge. It's a challenge for everybody. And there is, frankly, a limited capacity to process standards changes. It's a, you know, there's a finite amount of resources available to do that, even though we understand that it has to be done. And for the most part, each generation of aircraft has a significantly better safety record than the previous generations, and obviously that's something that we definitely want to maintain and potentially improve upon. So, you know, to keep up, it is definitely going to be a challenge that I think we're looking forward to meeting. And when we look at something like this, you know, the meter, if you will, of what is safe enough. And, you know, the expectations can change in terms of what people consider to be safe enough from year to year. And I think generally we would say that people expect things to be safer than they used to be. And in fact, they are. So, you know, there's the other aspect of that, which is, okay, now we have a new mode of operation. What level of safety is appropriate for that? And that's something it's interesting. It's very, very tricky to establish what is the appropriate level of safety if we have no history with it. So again, research for us, it's a foundational need. You know, we look at both what we need to do and what we don't need to do. The drivers, you know, from the standpoint of how things evolve, it could be new technology, it could be emerging threats, the state of the art technology. It may be a similar technology, but just refinement of that. And we may find service experience telling us that we need to do certain things. And again, if we have no service experience, then obviously that makes it even more challenging. So that's kind of what I just covered there, technology. And, you know, we have certain things that are assumed, but they may not always be true in the future. There can be new threats, things that we didn't have to deal with in the past. The environment can change. We might see a lot more air traffic, in which case there's, you know, the statistics will eventually shift on us. Or, you know, where airplanes or aircraft operate, if we start flying in between buildings on a relatively frequent basis, that's a different environment than what we've historically seen. So, you know, we're trying to, to the extent that we can, try to maintain awareness, try to engage, try to keep up with what's happening. We're attempting to move the standards so that they're defined so that people know what it is they're trying to do, but they also have enough flexibility to accommodate things that change. And that is easier said than done, but it's how we're trying to do it. And it's an international thing. I mean, this is really something that we have to work across industry and with other regulatory authorities in order to make successful. It's not something that we look at as a US or FAA only activity. It definitely has to be an internationally cooperative venture. And I think I've exhausted my time plus a little bit. So thank you very much for your attention.
Thank you, Jeff. I really appreciate the overview presentation. I think we have time for one question or maybe two. So I'm going to ask you, what do you see as the biggest challenge in keeping the regulatory standards relevant in light of technological developments?
Yeah, I think it's going to be keeping sufficient detail in the standard so that it's clear that you know, people can look at the standard and understand what they need to achieve with it, but also give it enough flexibility so that when there is a shift in technology or in again the method of or the mode of operation, that it's still accommodated. And we're looking at that right now to figure out the best way to do it, because we can see a lot of things coming that, you know, they don't fit as neatly into what we have currently on the books. So I think it's really going to be moving us to a you know, language that's performance-based enough that it allows for shifts in these different areas, but is still says enough that it's clear what the objectives are.
Thanks. I think we need to, we're going to stay on schedule if we move to John now. So thank you, Jeff, very much for your time.
Thank you.
Okay. Our next speaker is John Harris, and he's with the Boeing company, and he's going to be discussing understanding the impact of UVC light exposure on aircraft interiors. Dr. Harris has been with the Boeing company for over 23 years and is an associate technical fellow in Boeing Research and Technology. His initial project was the design and development of luminescent coating system that's still being used today to record the distribution of pressure across aerodynamic surfaces during wind tunnel airflow. Later projects include heat-resisting material systems for the 787 program and developing a novel flame retardant coating for in-surface insulation blankets and software for the rapid characterization and visualization of microcone calorimetry raw data. He has been awarded 19 patents, and he is involved in the Confident Travel Initiative project within Boeing for the development of mobile UVC disinfection technology for payloads interior applications. Please, John, thank you.
Well, first, a big hello to our fire safety family out there, wherever you are. Thank you for joining. I'm John Harris with Boeing. There's a lot to sort of talk about. This sort of got shoehorned into this meeting, but there is some discussion on flammability. The focus of this presentation is understanding the impact of UVC light exposure on aircraft cabin materials, and I will go through what that exactly means. So basically, the travel restrictions imposed by the COVID-19 pandemic, along with a reduction in traveler demand, has impacted the aviation industry. In response to this, the Boeing company formed the Confident Travel Initiative, designed to improve and mitigate any issues associated with safety. It's a large group of people, a very, very smart group of people working in a collaborative fashion with across industry, really, airports, airline customers, regulators, even infectious disease experts and other scientists. So its design purpose is to basically promote improved safety wherever possible, and basically promote improved confidence in travel. So at a high level, the Confident Travel Initiative is a layered approach. There's 3 layers described right here: prevent the virus from reaching the airplane, keep the airplane free of viruses, minimize transmission of viruses on the airplane. The 3 time horizons, I'll only be talking about the near term, which was a response to the immediate needs. Again, we put together a team to build something that we have been designing and trying out, and now it's being licensed. And I think you'll find it interesting. This is just a single slide. There's so much about confident travel. I don't have time. Basically, it's a more comprehensive approach to safety in air travel. Yes, there are different groups within confident travel, such as the group I'm in, that looking at UVC disinfection, but we also looked at antimicrobial coatings, and we also looked at disinfecting solutions, and we also looked at fogging. But in addition to that, there's other things like check-in, self-evaluation, enhanced procedures. So just to give you an idea of the scope and the magnitude of what we're involved with. Now, let's talk about what we're involved with right here, which is let's use UVC light to disinfect a surface. What is UVC light? UVC light is basically a range of wavelengths between 200 nanometers and 280 nanometers. And, we've been using this for years for surface disinfection. In fact, the 254 nanometer emission, for example, by a low pressure mercury lamp, has been used for decades for surface disinfection. The issue with the 254 is the 254 photon has a lot of energy, enough to break bonds, enough to kill viruses, but it also penetrate into tissue, specifically mammalian tissue. And what attracted us about the 222 nanometer light is that the 222 nanometer photon, it's higher energy than the 254, but because it is so strongly absorbed, it can only go and penetrate mammalian tissues, maybe a couple of micrometers at the very most. And so what happens is with the 254 nanometer photon, it penetrates through the membrane into the nucleus, causing DNA damage, mutagenic effects. The 222, we have some promising early results from universities such as Columbia University and Hiroshima University that targeted mammals, I guess, mammalian subjects, after long exposures to this light and looking for any sort of mutagenic damage or things like cataracts. And so far, at least, touch wood, the results have been promising. So what did we want to do? Well, we wanted to basically see if we could develop a system, it really is a system, to disinfect the inside of an aircraft, in particular key surfaces, galley, lavatory, main cabin, even work with the flight deck. This presentation is only focused on the main cabin, the galley, the lavatory, and the crew rest, because from my study, our inputs were basically a set of materials selected from those areas. In addition to that, we worked with a very, very clever, very smart team of individuals who put together a very robust light source with an emission centered at 222 nanometers. Specifically, it's a krypton chloride lamp. It's an excimer lamp. And we expose samples in a manner that simulates 25 years of in-service. And what do I mean by 25 years? I'm going to show you. We have to make some assumptions. And so there's a little bit of tutoring here on various terms and meanings. The output, of course, was, okay, after exposure, simulating maybe 20 to 25 years of in-service disinfection, what's the impact on the performance, mechanical properties, visual properties, and it's not listed, but I need to list it, it's flammability properties, and I'll be talking about that. Okay, so here's just a quick snapshot. Inside the cabin, what did we choose? Well, obviously, high-touch surfaces that might be touched by individuals and lead to fomite transmission. And so you're talking about the windows, you're talking about tray tables, you're talking about armrests. Dust cover, for example, polycarbonate material, that's a well-known polymer. That was one of our samples. Decorative laminates, you may touch the sidewall, PVF film, trim strips, stow bins. Of course, when you're loading your luggage, you may be touching and brushing the side of the stow bin. Seats, leather, wool, nylon upholstery, textiles and fabrics, floor mats and carpets. What we feel is a very representative, very large and very comprehensive set of materials that we tested. Okay, so now some quick lessons on photophysics. Essentially, how do we go about a study where we need to quantify the amount of light delivered and the amount of light received? Okay, so when you have a lamp, you turn it on, it emits light. Our krypton chloride lamps emit, and it has an intensity. Another name for intensity is irradiance. Basically, think of that as the number of photons per second per unit area. In this case, that unit area is a square centimeter. So that's the amount of light delivered. And the units are milliwatts per square centimeter. Another way of looking at a milliwatt per square centimeter, though, it's a millijoule per second per square centimeter. And that's how we get to the amount of light delivered. So assume, just as an example, that the intensity or the irradiance, whichever you want to call it, we'll call it irradiance, that the irradiance of the lamp is 1 milliwatt per square centimeter, and we hold it over this area. Assume that dashed line is just a square centimeter. Use your imagination. But basically, if we hold it over that for 10 seconds, we now have 10 millijoules of radiant energy absorbed by that surface. And this is something that we routinely recorded and measured using a commercially available power meter from Thor. Now, in our particular study, the lamp irradiance from our lamps did range between 1 milliwatt per square centimeter and 1.5 milliwatts. And again, we typically recorded the irradiance along the long axis of the lamp, and we had samples within roughly about 2 inches from the lamp. So pretty good intensity. Okay, so how do we then go about estimating 10 years of exposure? So for that, you have to go back to a term called lethal fluence. Lethal fluence is how much light does it take to kill the virus? And we're not talking about any virus. We are talking about the SARS-CoV-2 virus. Now, in studies done at other universities, and I'm going to refer directly to a study recently done at Hiroshima University, they reported a lethal virus at a log 3 kill of 2.7 millijoules per square centimeter. Now, for everyone here, log 3 kill is 99.9% of those viruses are dead. Okay, So we then rounded up, because at Boeing, we love to round up. We like nice whole integer numbers. We said, okay, that's a good estimate. Let's say an airline is using UVC light to disinfect and they want to kill the virus. So let's also assume now, just in this example, that their lamps have an irradiance of 1 milliwatt per square centimeter. Okay, you need 3 millijoules to kill it. So that means 3 seconds. That's it. So you hold the lamp at the point where it's 1 milliwatt per square centimeter over the surface, wait for 3 seconds, boom, you move on. That area is clean and virus-free. The other assumption we make is, how many times would the airlines do this a day? We thought was reasonable was, let's just assume it's 4 times a day and 360 days a year, and it's not hidden there, but basically let's assume it's over 10 years. So for each day, 3 millijoules for every time you apply a UV dose that's lethal. 4 times a day means 12 millijoules per square centimeter per day times 3,600 days, equaling 10 years. And you see that number in the bottom there, 43,200 seconds. That's the estimate we have of the amount of radiant energy falling on a surface that would simulate roughly 10 years of in-service disinfection. And if you then say, okay, well, our lamp is in the hood. If we turn the lamp on after 1 hour, we've got 3,600 millijoules per square centimeter, right? Assuming 1 milliwatt per square centimeter, assuming 3,600 seconds in an hour, that's 3,600 millijoules per square centimeter. So we now have a way of testing in the lab, in the hood, where it's safe, what the exposure would be to estimate years and years of in-service disinfection. Okay, now this is a picture of actually inside the hood. We did all our work inside the hood, even though the research suggested it was relatively safe, or at least the results were promising. We can't assume that. We all wore PPE. Everything was done in the hood, just to keep you away from anything like ozone. The hood wall, the hood window did absorb all that light. So what you're seeing is a small visible artifact associated with the lamp, but the 222 nanometer light is being absorbed. Nevertheless, we all wore goggles as well. So that's basically what you see in the middle here. That middle is the lamp mounted horizontally, and above it and below it, we have filters. And you can see on the plot on the right, that's what we get after filtration. So we get a nice narrow band of emission, and then we have a wire mesh grid sample platform, both above and below, which doubled our capacity for testing. Remember, we had a lot of samples from everywhere. So this is the approach that we did. Those are only 3 lamps. We actually used 6 lamps. Nevertheless, there was a lot of turnover. We tested a lot of samples and exposed them. Okay, that was tedious, but it was very, very important. So once we did the exposure, what did we do next? We performed performance testing. And that's typically mechanical testing, such as tensile. We did elongation. We did compression. We also did things like breaking strength and abrasion resistance, such as the Martindale method for textiles. Now, I'm going to summarize first thermoplastics. Samples included things from tray tables, kick strips, rub strips, floor mats, dust covers, finishes, the lot. And what was interesting is we did not see anything. We only had one sample material. It was a polyurethane, and its compressive strength, I think, dropped a little bit. It was statistically significant, but well above the requirement. Everything else was basically equivalent. We did not see any impact whatsoever. That's mechanical. Now for visual, we saw a range of results. Everything from hardly any change where you couldn't tell to something that had gone from bright white to severely yellow, almost brown. And then flammability was my biggest concern because, as you know, in the additive industry, you add these, basically, they're going to be throughout the sample. And I worried about oxidative degradation and the impact of oxidative degradation on additives that are at the surface. How would that affect something like vertical Bunsen burner on a sample that normally would easily pass? I'll just say with textiles, it's boring. We saw nothing, no change. Even we went out to 150 years with some of the materials. Very, 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 very durable. More durable, let's say, than normal usage. Carpets are exchanged typically every 18 months. So I call it a nothing burger because we didn't see any impact and we don't have any concerns at this point. We are going to do some more flammability testing though, so stay tuned. Okay, I chose as the candidate for flammability testing one of the worst performers for color stability. This is an ABS, so acrylonitrile butadiene styrene PVC polyvinyl chloride blend. It's not used very much and I'll just be honest, the only use I found of it is it's a toilet flush button in the laboratory. But because of its performance under light, I thought, well, this might be a good candidate to see if there is any impact. And what it'll say on the right-hand side is there was a small change in burn length. I think on the right, you're going to see something like 2.6 average, roughly. I mean, obviously, we did this at 20 years here, and we did it again at 30 years, roughly the same. On the left-hand side, that was the control without any exposure, roughly around 2.2 inches of burn length. The self-extinguishing time did become longer. It was 4.0 seconds on the control, and it was 9 seconds on the one that had been exposed. I think we did have one that was 7 seconds, but I think also on that second test that was 30 years, I think the controls actually self-extinguished almost right away. So there is a little bit of a difference there. Nevertheless, there's still a fair amount of margin between the requirement and how they actually performed. Just a quick snapshot of some of the pictures of the materials that we exposed. Again, I was quite happy and pleased to see that several materials, PVF, PA, PP, a TPU coating, not a polymer, but a coating, a finish, extremely well. And I won't name names, I probably shouldn't do that, but we were very happy with that company's TPU finish. The one that's hidden right now by the pictures is polycarbonate. Polycarbonate is everyone's headache, as you all know. And but polycarbonate did have a small change. Noticeable if you are putting something not exposed next to something exposed. Probably not noticeable if it's all changing at the same time. What you see on the bottom are the 5 worst performing polymers. The PPSU we knew, the polyurethane we knew, and of course the PVC. So there was no real surprise there. What was a surprise was the effect of dark pigment. White pigmentation, which of course our airline customers love, and we're not going to change, that's what they want. But that was the worst performing material. Typically, and here's the PVC copolymer. This is a material used in our tray tables. And if you used a white pigmented tray table material, you saw under 222 nanometer exposure, really severe yellowing only after an hour and a half. If you take that same tray table material and you incorporate a dark pigmentation, look at the change. We even doubled the exposure times. We wanted to see what the rate was over a short period, and that's why this slide is in there. You can really see that on some of the really fast-acting, fast-degrading materials, it's pretty significant. But the surprise was the impact of dark pigmentation, which when I thought about it makes sense because it's probably absorbing a lot of the extra light. Textiles, I have to show one slide just to say we did it. Again, no impact that we could find. We accidentally ran a sample out to 168 years, and that's the abrasion study on that seat fabric study. So, you know, unless you, yeah, I can't find anything. Basically, we shot at it as many times. We couldn't really destroy it. So that's a good thing. So recommendations going forward. Well, we still are looking at flammability. We're actually now working in a collaborative effort with the IUVA on a large group of companies looking at a more fundamental study, maybe even a slightly wider group of polymers. Our first phase will be basically polymers without pigment, and then we'll do the pigmented stuff that's being used. So stay tuned on that, that's ongoing. But we also have to look at this as an opportunity. We need to work with the industry to maybe look at ways to make some of our real good thermoplastics more thermal stable. So that's something that we're going to need if we adopt this method and it gets used with some regularity. The other thing is for our designers here at Boeing, I'm saying, look, if at all possible, if you can design parts using the PVF, the polyamide, the nylon, or the polypropylene, if there's not an issue with flammability, and there can be, but on some applications, you only need to meet vertical Bunsen burner, and so that's good. PVF is never an issue, but let's use those if we possibly do that. Finally, our thermoplastic polyurethane finish is a good short-term solution. It does have good flammability properties, and it was just solid as a rock under UV exposure. For future design, well, we might try to incorporate some more dark pigmented materials in selected locations if our customers are okay with that. We'll have to wait and see on that. And then when we need to be smart about design, because if we have, let's say, nylon around a stove in one area and polyurethane around another, you're going to see a difference very, very short term. So it's going to be very noticeable, and that's something that we're going to have to look forward to. So this is still an ongoing effort. I know you have a lot of questions. I'm probably at the end of my time, and I thank you for your time. And if there's time for questions, then great.
John, thank you very much. It's really interesting. In fact, I have a lot of questions, but what I'd like to ask you, would you be able to stay around till the break? And then if there are any questions, we could quickly cover them at the break. It's
How
only,
late? I can come back. I'm doing a meeting 12 minutes ago,
okay.
but I can,
Okay.
yeah.
If you can
Maggie,
rejoin.
We can
Yeah.
facilitate those questions via email if anyone has any questions for John.
Right, right.
Okay.
Thank you, John.
again, John.
Thank you.
Okay. All right. So I'd like to introduce our next speaker, Tom Fabian. He's the Global Technical and Innovation Manager at Underwriter Laboratories. And he's going to be discussing a very interesting topic, influence of 3D printing as safety critical properties, FR and electrical testing parameters. Tom Fabian was actually recruited by one of our other speakers, Tom Chapin, to join the fire research team at Underwriters Laboratories in 2004. He has since then been involved in areas including smoke detection, wildland fires, and upholstered furniture flammability, and has served on state and federal investigation task force. More recently, he's been involved in looking at the influence of additive manufacturing on polymer properties and the subsequent introduction of the UL Blue Card, which defines the additional requirements necessary to recognize plastics intended for 3D printing and 3D printed components and products. Tom has been an active leader in fire, plastics, and AM standards development community for 20 years, and he's involved in a number of FAA task force groups for additive manufacturing, the development of new fire tests for material certification. Tom, please proceed.
Thank you, Maggie. So I want to share a little bit about the 3D printing when we consider injection molding as a traditional manufacturing technique versus 3D printing. In injection molding, we have a fairly uniform density of the part, and you can see in that cross section of the 3D printed piece below that that's not what we have in a 3D printed part, right? 3D printing offers us many advantages to be able to create complex shapes and parts that are not possible through traditional manufacturing techniques. But there's an aspect of what comes along with it. So if I consider in an injection molded part that our molecules are well mixed throughout there, we've got that very nice uniform density and a very efficient energy transfer for mechanical properties. Within that 3D printed part, we've got that well entangled molecular level also along the deposited portions, but then we rely on cohesion to provide that energy transfer from between the adjacently deposited parts. And this is very can be seen very clearly on the mechanical studies that were done almost 20 years ago, where they looked at an injection molded ABS material and they observed a certain tensile strength. Then they took that material and 3D printed it longitudinally in the direction of our tensile bars and measured a different tensile strength, a lower tensile strength. When they took that material and printed it in the cross direction of our strain, they got yet a different tensile strength. And in this case, you can see that there's almost an order of magnitude difference from that same material, depending on how it's being printed. Well, if we see this showing up on the mechanical properties, then what happens on flammability, where surface roughness can lead to greater attachment of flame? In those channels that were created between the deposited lines, could that act as a chimney and accelerate flame growth within the interior if it's breached? So that's really where our questions were coming in at UL. How do electrical properties, ignition properties, and flammability properties of 3D printed materials compare to the injection molded parts? So we set out to do a study looking at these aspects internally. It's an internally funded study. We really wanted to understand how those properties are impacted, and then what does that mean in terms of material recognition programs and product certifications? And how do we extend from traditional manufacturing to 3D printed? To provide an overview of our research, we focused in on two materials that we could find. We found a flame retardant modified ABS material that was marketed as being a V0 rated material. And we looked at a $4,000 desktop printer for that type of print, for printing that material. We also looked at polyether, which is an inherently flame retardant material frequently used in aerospace. It requires a lot more control and not just control, but the conditions to print it are more severe than for ABS. So we looked at a $45,000 industrial printer. We wanted to focus in on the key factors that a user can adjust. So not looking at all the different factors that impact 3D printing, but just looking at build orientation, the direction that we're printing it, the raster angle, the angle that we're depositing the adjacently layered materials, the air gap, how close those adjacent deposits are being put down, and the layer thickness, or in this case, we're using the tip size of our material extrusion 3D printer to guide that. We looked at a full factorial with the centered design of an experiment, and to look at these different factors. But we took it one step further, where we took our filament and we sent it to our lab, chopped it into pellets, and then injection molded those pellets. So now we've got injection molded material that was made from the same feedstock as our 3D printed filament parts. And then we looked at a number of different electrical ignition flammability properties: dielectric strength, volume resistivity, comparative tracking index, high current arc ignition, hot wire ignition, and Ul94 flammability. So I'll start with Ul94 flammability. On the left is our ABS test results. Now I said that this was a V0 rated materials, how it was advertised. And when we look at our injection molded sample, which would be how that Ul94 rating was achieved, it was a V2 rating that we achieved. Now, that V0 rating is based on pellets that were injection molded initially, and that's where that V0 rating was established. However, those pellets were then subsequently extruded into that filament, which was then injection molded for our study. So that's two steps. Likewise, that same filament is being 3D printed. So again, it's two processing steps. So we've got two opportunities for thermal degradation to be occurring on these materials. So we saw that V2 rating already, which is already giving us an indication that pellets that are being used don't necessarily translate to 3D printed material for their ratings. When we did 3D print that filament, the ABS filament, we saw a wide variety of performance. Many of our 3D printed specimens out of our 30 different variations did achieve a V2 rating, but we also had a number of them that did not pass the vertical flame test. So that's a problem where that material, it's the same material, it was just printed differently, may pass, might not pass. And we found that build orientation was the key factor for differentiating on performance, whether it's printed horizontally or if it's printed vertically in the vertical orientation. Now, when we look at polyether imide, I show the results a little differently, and I'm showing the results of the 30 different builds and injection molding on the right side. And you can see all of our burn times are roughly around 2 seconds. They're slightly longer with the injection molding at about 3 seconds. So that's a little bit interesting because now we're seeing the injection molded sample burnt just slightly longer than our 3D printed ones. It's within the margins of our statistical tolerances, so we can't say that it's statistically significant, but just kind of looking at it on the whole. What we believe is happening here is that the greater surface area of that 3D printing is allowing that ether, or rather the imide moiety, to interfere in the combustion kinetics at a faster rate than in the injection molded smooth sample. And that's where we're getting a slightly shorter burn time. Compare that to the ABS samples where that greater surface area is allowing that inherently flame retardant, that inherently flammable material to burn at a faster rate. So again, build orientation is a significant factor though. When we look at high current arc ignition, so this is simulating between two live components, there may be some arc occurring when like a switch, for instance. So we're looking for up to 150 arcs being subjected to the surface of the material. Will it cause the material to ignite? And we found with the ABS material, regardless of how we printed it, or if it was injection molded, none of our specimens ignited. So they all get the best rating, best performance level categorization, which is great. With the polyether imide, again, we saw a very similar type of behavior. Out of the 150 specimens that we tested that were 3D printed, 3 of the 150 did ignite. Again, it was at such a high number of arcs occurring that it still leaves that print as being considered the best performing category. So we can look at 3D printing where it was significant on flammability tests. On a high current arc ignition test, we don't see a significant result impacted by 3D printing. If I look at hot wire index or a glow wire index as being a similar type of test, where we're applying an energized nichrome wire to our specimen and looking for the time to ignition, we are again starting to see results. All of our ABS samples, probably not too surprising, melt and drip away from the nichrome wire. So it would, by definition of the standard, get the best result. However, if we consider the length of time it took to melt and drip away, we are now starting to differentiate based on build orientation as being the most significant factor. Whether it was printed in the horizontal plane or in the vertical plane had the greatest impact. And within those different build planes, depending if we had a larger spacing or a smaller spacing with the layers and the air gaps, we could see different levels of performance. So again, how we print that same material did lead to significant differences in performance. Polyether imide, likewise, here we did see some of our samples did actually ignite. So some of our vertically oriented samples ignited, and we did have a decrease in performance. Now, this is a material that is frequently used in aerospace, so this becomes a question of what does this mean now for a given material when it's 3D printed? Is it safe to use or not? Now it's really starting to say it depends on how the parts are being printed that are going to be used. So again, it's a very critical question that's coming up. So I'm going to jump to comparative tracking index. So this is a test where the surface is being contaminated and we're looking for potential arcing to occur or tracking from one live element to another live element, or in this case, electrodes. Nominally, this test is conducted on a smooth surface that is free of surface imperfections. When we look at many of our 3D printing techniques, you have an inherent surface texture that is being put onto that material. How that surface texture can impact the results of this test come about by the liquid that is being dropped between these electrodes to create that tracking bridge. If the liquid, if the tracks on our surface are oriented such that they line from one electrode to the other electrode, like on the image on the left, it could cause the liquid to wick between the electrodes and reduce the energy required to cause the tracking to occur. Conversely, if that surface detail parallels the face of our electrodes, like on the image on the right, it could cause the liquid to wick away from the electrode surfaces, leading to what appears to be a higher tracking index from that test. And we didn't even get into what happens if the liquid can wick vertically away from the surface, right? That can create yet another orientation aspect. So in this case, we do have to look at, within the standard, to look at both directions. So we would have to look at both the scenario demonstrated on the left as well as on the right, as opposed to a normal test where on a smooth surface where that orientation does not become a factor. So again, I'm plotting out our ABS on the left and our polyether image on the right. Injection molding is on the right side of both of them, and then our 30 different variations of 3D printed samples. And if we'll focus on the ABS to start with, and we do see a difference where you can see, again, the Z orientation, which is in the third box. We're starting to see some significantly higher comparative tracking index voltages, indicating better performance, but it is the same material in every case. And that's actually the opposite of what we saw with the polyether image, where the horizontal ones in the X and the Y, the first two boxes, seem to be giving the better performance. We also likewise see that that orientation that we were just talking about does have a significant effect. And we found that when that track was orthogonal to the gap between the electrodes, then we would get a higher CTI when the deposits are being closer together. So we're getting the wicking occurring versus when it's parallel to that faceplate. So when they're parallel, we get the higher CTI, the liquid is wicking away from the electrodes, so we're not getting the bridging between the electrodes, and we're getting a higher CTI value. It's the same material, it's the same surface, all we did was rotate the surface. So this is definitely an artifact of the test method itself. We do see that build orientation is a significant factor, as I mentioned. And now it's starting to look like some of our 3D printed samples are outperforming the injection molded. And this becomes important when we consider where materials with these types of results can be used. Materials getting a performance level category of 4 can be used in an indoor application. A performance level category of 3, where we're now starting to see some of these Z orientation builds and the horizontal builds on the polyether image, is now starting to get into the outdoor, less severe use. And performance level category 2, which we do have in both cases, now you're getting into some severe applications of the material in an outdoor use. So now it becomes very important how the measurements are being done in order to reflect what the properties are of this material truly are to assess the hazard that is being displayed that we're trying to address. So I'm going to try and summarize here. First, we do see injection molding does give us more consistent dimensions than the 3D printed. And this makes sense from having a fixed volume cavity versus an open volume build. We do see greater consistency of the industrial grade printer versus the consumer grade printer. And you can see that on the images on the right, where the top image is the polyether image from that industrial grade printer versus the ABS on the consumer grade printer. You can see the bands occurring in the consumer grade that we don't see within industrial grade. Really, the additional money is getting you better repetition, more accuracy on the printers. And that can become a significant factor. If you don't take anything else away, this is probably the most critical one, is that the build settings do influence the results. That same material on the same printer can yield critically different performance. We saw that with the flammability. We saw it with the comparative tracking index. We saw it with volume resistivity. We saw it with dielectric strength. We saw it with the hot wire ignition. And in every case, we're seeing that if I take that material, I can alter my performance depending on how I print it. So that becomes really critical and has a big impact when we look at what does this mean for products that are being 3D printed and how should they be assessed for safety. None of our tests did we see where the 3D printed products, 3D printed samples outperformed our injection molded samples, with the exception of CTI, which, as I said, we believe to be an artifact of the test. So that's a nice thing to know, that if you are doing your testing and you're getting acceptable performance on a 3D printed prototype, moving to an injection molded one should only make things, will be at least as good, if not better. So it's a nice place to be. UL is working with both our standards technical panel and IEC to look at how do we update standards because of 3D printing. It's really introducing a lot of new variables that have not been addressed through relatively simpler test specimens. So what does all this mean when we put it into practice, right? How do we use it for a 3D printed material or 3D printed product? First, we have to take a look at the UL recognition cards, the yellow cards. And this is something that UL has been using, introduced back in 1959 was the oldest one I found. And now there are more than 47,000 materials that are registered. And so any user can go in and look at, based on the material and the grade, what kind of performance can be expected for a given thickness, which is very nice for all of our traditional manufacturing techniques. As we saw though, however, what happens when you change that printing parameter? So we haven't changed the material, we just changed how it's being created, the specimens. And how do we capture that type of information? So we moved into a new system. We kept the yellow card for our traditional manufacturing, but we introduced the blue card. And the blue card is specific to the additive manufacturing. And I list out the 6 different techniques that are used for plastic materials. And I'll give a brief overview of what a blue card captures to be able to serve that same function as the yellow card. Just like the yellow card, we're still keeping the plastic and the grade name and the performance characteristics all in the top portion. When we get into the bottom portion, now is where the difference is coming in. First, we're indicating what processing technology is being used for 3D printing. The different techniques will rely on different aspects. What are the user controllable parameters that are being used to make these samples that are evaluated? The build plane, the layer thickness, the infill, the raster angle, the print speed. These are all settings that you as a user can typically alter when you're printing. Finally, is any post-processing required? Material extrusion, you might not need post-processing. Vat polymerization, if you don't do post-processing, you're going to end up with a gooey mess at some point. Finally, I mentioned the model printer. Printer models do matter. We have found that even when we use the same parameters at the same material, we will get different results depending on the model of printer because of how they work. So that becomes a significant factor. So the end result, though, of what we're capturing on a blue card is if I use this grade of material on this printer and I use this printing parameter combination, then these are the results that can be expected. So we're going back to the same purpose as what the yellow card serves, of being able to predict out what the properties are to allow the engineers to be able to use those properties for their design purposes. It also now opens the opportunity for us to look at a 3D printed product and how to evaluate that 3D printed product for safety performance. Critical aspect when we do this, however, is we need to look at how do we collect our samples? And this is a really critical difference of what we've seen compared to many other aspects. First, we look at horizontal and vertically printed orientations because we've seen that to be a significant factor. We do look at having samples cut from different angles so that we have an orthogonal set because we do see that as a significant factor on our builds. We've also gone to cutting samples from a printed sheet. So whereas in injection molding, you may be directly molding those samples, now we want to put a sheet and cut off the edges because we do see, particularly with some of the techniques where you print the contour and then you infill the sample, that contour does play a significant role on the results. And yet we're trying to replicate what may happen in a different system, so we eliminate those contours. And what we'll report then on the blue card is, what is, let's say for that horizontal plane, what is the lower of the two values? That's what gets reported on a blue card. So now that we have a nice technique for capturing that information, we can go into looking at how do we certify a 3D printed product or some component. First, we have to acknowledge that ultimately it's the performance of that component that matters. Doesn't matter how we made that component, but whether that component is performing. So the performance requirements are the same, whether it's 3D printed or made through traditional manufacturing. That does not change. If the material has been done through 3D printed using a blue card recognized material, then we can ascertain whether it was being printed using the same parameters and model printer as what's listed on the blue card, in which case we can expect that performance as what's reported on the blue card, and it can be assessed based on it. If not, we treat it just like any other injection molded part using an unlisted material, where we're going to do the material performance test also. An important aspect when we look at 3D printed parts is, how do we look at the part in terms of the thickness? So I show a cutaway diagram here of a 3D printed part where there's a lower density infill for weight savings purpose, and a thicker contour around the exterior and around some of the interior components. So what we want to consider is, what is the thinnest section that is exposed to the elements? And if that thinnest section is not compromised, then we don't worry what's behind it. So in this case, if we had our electrical components running through the holes or on the exterior, you can see there's a thicker contour. So we're only concerned that that contour is not breached, that contour has the performance required for that product. We don't worry about the infill, which may be thinner. Important aspect on this is the direction right now being led by the FAA, since we're focusing on aerospace. With the FAA, it's not just the contour that they're concerned about, it's the contour plus the infill. And Stephen Wren has reported some fantastic work, actually just last week at the FAA's tri-meeting, where he was presenting results on how that infill density will influence results. Keeping the same infill density, but changing the thickness of these infill walls will also influence your flammability characteristics. And in previous work, he demonstrated that the pattern that's used. So here we're using a cubic lattice for that infill, but if we use the hexagonal packing, even if the infill amount is the same, the geometrical effect introduces a consequence on the burning behavior. So that is something that you do have to keep aware if you are 3D printing parts for aerospace.
Hey, Tom,
So you do have to consider your samples differently.
Sorry, this is Brianna. I hate to interrupt, but we actually went right through the break. But I did notice there was interest in your presentation, so we went ahead and just, let that be. But I did want to remind everybody that you will get a copy of the session slides and recording in case you do need to step away and come back from the session. So Tom, if you don't mind just wrapping up, and then we can stay on schedule with the rest of the speakers.
Yep, absolutely.
Thank you so much.
Thank you.
Thank you, Tom. This is Maggie Bauman again. There have been several questions, so I'm assuming we will try to answer those questions at the end of the session or with direct questions to Tom. Okay.
Yeah, Maggie, I also saw that John was able to join us again. So what we can do is just facilitate those via email or save those until the end. And I'm happy to help you facilitate those at the end.
I wrote the one for John down, and now I wrote notes on the rest of these. So thank you. I appreciate that. So we're going to introduce our speaker from Safran cabin at this point because, and as Brianna said, if you need to take a break, please do so. The topic for Bhaskar is flammability and fire properties of composites used in aircraft interior structures. Bhaskar is the Director of New Materials Development and Process Engineering at Safran Cabin in the US. The primary focus of his job is to lead the development and engineering activities for composite materials and structures in aircraft interior applications. His professional journey has taken him around the world, and so he has been able to involve his expertise in the technical development and advanced manufacturing solutions for improving production, performance, and growth. Bhaskar, please proceed.
Thank you, Maggie. Can you see my screen?
That's great.
Hello, everyone. My name is Bhaskar Biswas, and my presentation is focusing on flammability and fire properties of composites used in aircraft interior structures. As you can see, the present title slide shows 3 pictures and each of them showing a scenario. The picture on the left shows a possibility of burning an aircraft. Picture in the middle shows an aircraft burnt halfway through, and picture on the right shows it is possible to evacuate the aircraft before fire spread. So if an aircraft catches fire and the fire is somehow has got slower propagation, then it may allow time passengers to evacuate. Therefore, the overall aim for the present manufacturer is to improve fire resistance of aircraft through preventing ignition and propagation of fire. Before I go into details, I would like to give an overview of the presentation. Application of composites in aircraft have grown significantly over the years. So first, I would like to show where composites are used in aircraft interior structure. Then I'm going to talk about importance of fire properties of composites for the application, where legislative requirement plays an important role. Since regulatory requirement of fire properties is very important, I'm going to talk about how manufacturer or industries take approach in order to meet this requirement, and what type of preventative measures are used to reduce this probability. And also, I'm going to talk about the technique are used to measure the performance of the material. And finally, I'm going to talk about certification processes. Now, the first one, application of composites in aircraft interior structure. Since composites are known for high strength to weight characteristics, application of composites in aircraft have been growing significantly in order to improve the fuel efficiency. As can be seen from the current slide, composites are used in interior walls, monuments, in some equipment, some structures, and in passenger carrier. And here are some examples for each application. As you can see, composites are widely used in aircraft. Therefore, fire properties of composites are taken very seriously. So the reason for that, and I would say the primary reason for taking fire property seriously is there is a very limited or no egress option available to passenger and crew in the aircraft. Here is an example. Continental DC-10 caught fire in LA airport in 1978. And as you can see, the fire was severely propagated. Having examined fire-affected sidewall liner of the aircraft, it was found the exterior wall of the panel was badly burned or damaged, whereas the interior wall of the panel was much less affected. So this suggests fire retarding performance of material can prevent the propagation, to prevent the fire from propagating, and which will allow time to evacuate the aircraft. So, as learned from many aircraft incidents happened due to fire, important control for the reduction of the effect of fire is to delay ignition and propagation of fire, so that it will allow time to fight the fire and saves lives. So there, 2 prerequisite missions are taken into consideration in order to improve the fire safety. The first mission was, our first mission is to prevent in-flight fire so that passengers and crew are not exposed to the fire directly. Here is an example of Air Canada, which caught fire from outside, and there is no fire inside until it landed. And the second mission is to delay cabin flashover. And the picture in the bottom shows an incident happened in Manchester in 1985, which had delay in flashover and allowed passengers to evacuate the aircraft. So in order to pursue this mission in practice, an enforcement was required to make sure all the components are safe. And in order to do that, it has to be done in the manufacturing level. This has led many aviation agencies to come up with regulatory requirement. So aviation agencies like agencies of federal government has come up with legislation of regulatory requirement by publishing Code of Federal Regulations, where number 14 CFR covers aeronautics and space, and part 25 of that CFR includes the regulation for fire safety. So in order to support the regulation and support the manufacturer, FAA also came up with a policy statement, which is a method of compliance, and it dictates how to meet regulatory requirement. Here is an example of a panel. The policy statement says the panel must pass Bunsen burner test, and also it has to meet heat release requirement and smoke density requirement. Similarly, there are other 25 components used in aircraft, and the policy statement gives details for each of them, how to meet this requirement. Since the regulatory requirement is stringent, the industries had to take pragmatic approaches to meet this requirement. And the very typical approach they take is to use materials that are inherently fire retardant. Typically, phenolic resin and composites made from phenolic resins are the prime example. Also, by selecting material that have higher autoignition temperature than service temperature. Also, by using non-flammable material where possible. Sometimes it is possible to mask components with fire retarding material. And also sometimes it is done through changing design that allows a reduction of fire-prone material. And the last one is to impart fire retarding characteristics to non-complying polymeric material using fire retardant chemical. And this one is very important because there are some polymers which are very demanding and cannot be used in aircraft because of the lack of fire resistance property. And for those polymer, these steps is taken in order to improve the fire resistance properties of the material. So as mentioned in the previous slide, industries do fire retardation of materials. And the reason for that, mainly three reasons, I'll say. The first reason is doing that, it provides thermal stability to the material. That means resistance against heat generated from fire. The second one is it helps to hold integrity of the composite. That means it may ensure the material doesn't degrade or disintegrate or any material doesn't fall off. So that is what done. And then the last one is isolation of fire in order to reduce the intensity of burning. So there are different type of fire retardant chemicals or chemicals used for fire retardations. So these are as follows: fire retardants, intumescence, and smoke separations. And within fire retardant, there are two types of fire retardant: additive type fire retardant and reactive type fire retardant. So here some examples you can see, and the following slide will give further details. So there are different types of fire retardant, and it is not easy to select which one to be used for the material. And that's why sometimes it is difficult for industries, and then industries come up with a strategic process, and that is material selection process and process selection process. The very first process industries take, that is material selection process. And in this selection process, the first one industries consider fire safety of the material, then manufacturability of the material in order to ensure material can be processed consistently over the time. The third one is component specification to ensure it meets all the design requirement. And the last one is the customer specification to ensure if there is any additional requirement from the customer. Once the material selection process completed, then industries go through the steps and go through the steps to find out what consideration need to be taken for the processes. So for the processes, the following factors such as level of complexity, processing time, process parameter, human interference, and overall processing cost. Upon completion of formulation and modification of the polymer, then it is important to ensure which test technique to be used for the assessment of fire performance of the material. And the current slide shows there are a number of tests can be used for assessing fire performance of material. So here are the type of test, and each of these tests comply with respective regulatory requirement. OEMs like Boeing and Airbus, they have their own test specification, and each of these test specification meets respective regulatory requirement. For composites, there are mainly three tests are used for composites, and these are 60-second vertical burn, OSU heat release rate measurement, and smoke density measurement. The following slide will give more detail of these three tests. So before starting any test, it is important to make sure what type of material or what type of sample construction to be used for the test in order to ensure or in order to get more accurate information from the test. And the typical constructions are used for this type of test are monolithic laminate construction and sandwich panel construction. In monolithic laminate constructions, mainly 2 ply laminate and 4 to 6 ply laminates are used for the test, whereas in sandwich panel constructions, 1 ply core, 1 ply 1/8 inch panel, and 2-ply core, 2-ply half-inch panel are used for the test. Then in the test, first it goes through the flammability test, where the sample dimension is 12-inch by 3-inch for the coupon, and the orientation of the sample 12-inch side is held vertically. Here is an example of flammability chamber, vertical flammability chamber, and the information collected from vertical flammability chambers or vertical flammability test are burning time, burning length, and drift extinguishing time. Next is OSU heat release measurement. In this test, the sample dimensions are 5.94 inch by 5.94 inch, and samples are vertically held. And here is a picture of OSU calorimeter, and picture on the left or a schematic shows how the sample is held vertically against the radiant plane. And the graph in the bottom shows a typical trend of OSU curve when it gathered the information, or it plots the information of heat generated from the material when it burns from different phase, from the non-flaming phase to fully developed fire phase. And from this curve, the information we collect are peak heat release rate and total heat release in first 2 minutes of the test. And the test, usually it is carried out for 5 minutes. Then smoke density test. And in smoke density test, sample coupons are 2.9 inch by 2.9 inch. Samples are held vertically. And here is a picture of some smoke chamber. And the information we collect from this test is the optical density of smoke at 4 minutes after inserting the sample. So once all the tests are completed, industries go through a very important process, conformity and certification process. These processes are very important because for the manufacturer, because it is to ensure that industries are producing quality product. In these processes, basically what we do when a material chosen to be used in composites for the application, it goes through a number of stages. In the first stage, which is the material selection stage, one batch of materials are tested, whereas in material qualification stage, 3 batches of tests done, and in certification stage, one more batch of materials are tested. Here, not only these, also materials are tested in different level of structural assembly, from material to subcomponent and at component level. Also, the qualifying requirement in lower level of structural assembly are tighter as compared to that in final assembly level, as you can see from this table. Finally, since fire safety is the highest priority for the aircraft interior part manufacturer, therefore painstaking processes are performed for the component of composites in order to make sure safety of aircraft, hence safety of crew and passengers. Thank you. And my special thanks to Safran, SAMPE, Pinfa, and Clariant for supporting to make this presentation happen.
Thank you, Bhaskar. I'm going to give you one question. We don't, oh, wait a minute, here's a question from the group. Let me give you that one. Okay. So why are the typical constructions of laminates and panels considered for the fire testing?
Okay, I'd like to go back to the particular slide, and I'm going to show. Right. So if you see, the constructions are used 2-ply laminate and 4 to 6 ply laminate. A 2-ply laminate is the worst case scenario. It catches fire very quickly and burns very fast. So that's why we consider the thin laminate is worst case scenario, whereas 4 to 6 plies are quite common in the application. That's why we use monolithic laminate construction like this way. And then for sandwich panel, again, the 1/8 inch panel, which is 1 ply or 1 ply, that is thin panel. And that is also worst case scenario. That's why we consider this thin construction, whereas 1/2 inch panel is quite common for the application. So that's why we take this type of construction for the test.
Okay. Thank you, Bhaskar. Will you hang in there with us till the end in case there's some additional questions? Will you be able to stay?
Yes.
Okay, thank you. All right, so to stay on schedule, I would like to introduce our next speaker, Matthew Blais with the Southwest Research Institute. This presentation is very interesting because it shows the difference with comparative room burn studies of furnished rooms from the United Kingdom, France, and the USA. Dr. Blais is with the Southwest Research Institute. He's the Fire Technology Department Director, and he manages a group of approximately personnel providing fire resistance testing, material flammability testing, and research in fire technology on a wide range of projects for both government and industry. His experience includes evaluation of toxic smoke characteristics in fire testing, catalyst design and synthesis, weapons of mass destruction, counterterrorism, consequence management, materials research and testing, and demilitarization of chemical weapons. I'd now like to have you proceed, Matt. Thank you very much.
Thanks, Maggie. I'm going to kind of change pace a little here. We're not going to talk about aircraft so much as the impact of country fire codes on the safety of the furnishings that you have in your home as a result of those standards. And we're specifically looking at the United Kingdom, the United States, and France. So there's a couple of myths out there about fire retardants. The standard myth is that they don't really work. Every test we do shows how they work. They prevent ignition from small ignition sources. They slow the rate of fire growth when a larger ignition source is present. And they allow for the extinguishment of a fire early on or the escape from the building, saving lives. The other big myth out there is that fire retardants make more toxic smoke. It's just not true. The action of the fire retardants in slowing the growth rate of the fire reduce the amount of material that's burned in an anoxic environment or a low oxygen environment, therefore getting more complete combustion, because it's the products of incomplete combustion that are the most toxic in smoke. Modern polymers especially are very flammable, burn very quickly, consume all the oxygen, and a lot of PICs are produced per mass burned. Talking specifically about this experiment, we took furniture produced for the 3 different markets by the same manufacturer. We equipped rooms with the furniture, added a couple of extra things. So we had TVs, a couch, and a chair from the market that we're studying, but the extra stuff in the room, like the bookcases and the tabletops, the file cabinet, those are all pretty standard items that we got from Walmart. We did a series of 3 burns of each room source. In other words, 3 for the United Kingdom, 3 for the United States, and 3 for France. We performed ignition of each of the individual rooms with progressive ignition sources. We used the BS5852 ignition sources that you see aligned in the upper right-hand corner of this picture. You have the BS5852 crib 4, 5, and 6. 4 being on the left side, going to the right to the 6. They increase in size and the total amount of energy that's being released and the rate at which they're released. All the cribs were placed in the same location on the couch in the center cushion towards the back. We performed a lot of different analytical. We collect smoke and did a lot of studies on smoke, but we also looked at heat release rate through oxygen consumption calorimetry. We measured smoke through light obscuration, and we collected video and infrared evidence. The analytical analysis we did on the smoke itself as we collected it covered a wide range of analytical techniques. You can see from the photograph how much was going on for each experiment. The first test of each country code, we collected 1 sample for the duration of the burn, whereas the second and third test, we tried to collect smoke in the early stage of the fire and in the late stage of the fire, where we saw a white smoke versus a really black smoke. And that's what's shown here. So a total of 9 rooms, 3 for each country, 1 each ignited with a crib 4, 5, or 6, and all ignitions were on that central cushion. So this is kind of what that looked like in the stages that we were talking about. You see in the top part of that picture, the smoke is very white. That's an early stage of ignition. It hasn't gotten to the point where there's a lot of consumption of the oxygen, whereas the lower one, you see how black the smoke is turned. That's a function of the fact that the materials now are being produced at such a fast rate that the oxygen's been consumed, and there's a lot of non-combusted material in that mix, the products of incomplete combustion. So I'm going to show you what this looks like in the same time frame of simultaneous burns. So you have, as shown, US, Great Britain, and France located from left to right. These are all on the same time scale. You're already in flashover on the 2 on the outer edges, whereas the fire is slowly growing in the middle. As soon as it reaches the edge of the cushion, surface area starts to accelerate the burn. This will eventually reach flashover, but it takes about 18 to 20 minutes to get there. Whereas the other rooms are completely burned out by the time the center room, the Great Britain, UK room, reaches flashover. And there it goes. So what does this look like measuring the heat release rate? You can see in the crib 4 case, 3 to 5 minutes in, you're at flashover for both the French and US room. And the same thing is true for crib 5 and 6. The time scale didn't change very much, even though more ignition energy was used. You do see a slight difference with the UK rooms, where the gray line is shown in those. It's a much later transition to flashover, but the larger the ignition source, the earlier that tends to happen. But it's still at least 17 minutes of escape time before you actually reach flashover. So opacity measurement, you see the same sort of effect. You're at 23 minutes before you get any obscuration with the crib 4. It says 18 minutes and about 19 minutes for cribs 5 and 6. What that really means is the air is clear enough you can see your way out of the room, escape easily. It's a very important factor as far as escaping the building, what you can see to get out. So opacity here was delayed significantly for the UK room, which has the highest standard for fire retardancy in furniture, and obviously is a pretty good standard. So smoke characteristics. You can see that we have white smoke and black smoke that are developed as the burn progresses. The white smoke has a very different chemical composition than the black smoke. The black smoke has a lot more PICs, and as a result is a lot more toxic. And you can see that transition occurred in the previous slide at 17 to 19 minutes for the English furniture, whereas the French and US, it was 3 to 4 minutes into the burn. If you think about what your fire alarm in your house would do to go off, you're basically just waking up when the smoke is heavy in the room, there's lots of heat, lots of fire, and you're unlikely to escape a US or a French constructed system, whereas you have plenty of time to get out with the UK. And again, as I said, the white and the black smoke are very different chemically, and we'll look at that. Just looking at FTIR analysis of 2 locations within the room, we see very different performances of the French and here are the English room, the UK room are shown. You can see that you're extremely toxic in about 7 minutes for the French room. The carbon monoxide goes through the roof. Hydrogen cyanide is very high, whereas the toxicity of the UK room at the bottom sketch down there on the right-hand side, you can see that the toxicity of the smoke is much delayed. You're all the way out to 20 minutes before you see any toxicity at all in the smoke. So obviously it's much easier to escape. You have more time to do so. And the toxicities in the French are enough to be lethal with basically one breath knocking you down. We did a lot of other analyses. We looked at volatile organic compounds. I'm not going to go through all of this because it's an eye chart, but you can see that the highlighted ones, the bolded chemicals, radically differ from the UK rooms to the French and the US rooms. You see a lot lower production of the very toxic chemicals in the GB room pre-flashover, and that's a lot longer period of time to escape. So your exposure to the smoke is somewhat limited, and as a result, you're not going to have near the severe health effects you would for both the French and the US rooms. And we see that same sort of thing with SVOCs. I've primarily listed here the PAHs, the polyaromatic hydrocarbons. Those are the chemicals of concern in smoke that will cause cancer. The larger molecules like phenanthrene, anthracene, fluoranthrene, pyrene, and benzopyrenes especially are the ones that cause the biggest problem. You see very, very little of that pre-flashover for 20 minutes inside of a GB UK room. But as you get past flashover, you start to see more of it, but they're nowhere near the numbers that you see for the US room. And on the next slide, we have, sorry, skip one, the French rooms. You can see those numbers are quite high. So the bottom line is the English furnishings, the UK furnishings have lower molecular weight and lower concentrations of the PAHs, whereas the French furnishings had the highest, and the US was somewhere in between, but still very high. The black smoke is much more toxic and is produced much earlier for both the French furnishing and the US furnishing than for the UK. You have all that time to get out, so your exposure is going to be much less. We looked at chlorodoxins and furans as well. We looked at chloro and bromodoxins and furans. There's not much story to tell here. We really didn't see much of anything that was of any concern. And again, these are the bromodoxins. So we wrapped that all up. We published all that work. And then we actually did a toxicity study because we collect full smoke samples over the entire duration of all the burns. And we did cell line exposures looking at toxic effects. That's published under a separate cover. But this is the, we actually got to repeat the fire tests recently in January. And we did it differently. Instead of using a standard 9705 room, we had the entire long wall open. And we were looking to see if that would affect the way the room burned. Interestingly enough, it didn't at all. We got about the same results as far as flashover. And you can see that we put out the fire on the left, which was the British room, with a fire extinguisher, whereas we had to use a hose stream to put out the one on the right. So the conclusions, the country codes do play a critical role in fire safety for furnishings and home, especially furniture, which has so much energy content. The BS 5852 standard is probably the best furniture standard in the world. We see at least 4 times the performance in the amount of escape time for the BS 5852 rooms. You can also see that the smoke toxicity in the highest flame resistant case actually had the best performance for smoke toxicity. The lowest toxic smoke was produced both for the polyaromatic hydrocarbons as well as for carbon monoxide and hydrogen cyanide. So this is also this is acute toxicity as well as chronic toxicity. So the fire gases that will knock you out and kill you, the narcotic type gases are much lower in the UK room, and as well as the PAHs, which could give that long-term health effect, were much lower. So fire retardant materials actually do produce less smoke, and they're more highly protective in the English furniture. So it's much more survivable type fire. So the process that we see going forward with people trying to eliminate fire retardants from home furnishings is probably ill-advised. The technology does add value and reduces risk from fire. And that's the end of my presentation. I went very quickly.
Thank you very much, Matt. I think it's a very compelling argument for the value of flame retardants in application. And therefore, that's why I find this data so fascinating. And we wanted to include it in this group of presentations. I'm trying to see, we have a question. Uh-oh. I have a.
It just said my first name. There it is.
Oh,
Okay.
yes, here it is. Do you know whether these furnishings were flame retarded by halogens or now non-halogenated flame retardants?
We did go back and analyze. Ammonium polyphosphate was in the UK. There were no halogens in those furniture.
Okay. Were there halogens in the French and US?
No, they had no fire protection that we
No
could
fire
detect at all.
Okay, absolutely.
The televisions that were in the rooms did have brominated fire retardants in them.
Okay, thank you. Let me see, how are we doing on time?
Hey, Maggie, if you want to roll right into the next speaker, we can go ahead and do that. I see a question coming in right now from Bernardo, so maybe we'll give him a second.
Okay.
Excellent presentation, Matt. Very interesting. Thank you.
Well, it's very visual, you know, that's what we need. And we need to have these kinds of examples to show the value of flame retardant technology as in polymers.
Absolutely.
I don't see it. Oh, are these videos available? Matt, would these videos be available? I mean, this presentation might be available, right?
The presentation is available. I can provide videos. I have tons of videos. We've done tremendous number of comparative burns. So if they're being used for the right purpose, yeah, I'll provide them.
Okay, thank you.
Thanks, Matt. This is Brianna. You can send those right to me and I can distribute those to the registrants.
Okay, you'll have to download them because they're huge.
Fair enough.
Okay.
Thanks.
Okay, so with your permission, Matt, I'll move on to our last speaker. Certainly not the least. Tom Chapin is going to speak with us today about improving battery transportation safety, which is a very, very hot topic in a lot of markets today. So Dr. Chapin is a UL William Henry Merrill Society Corporate Fellow, and he's past chairman of the UL Fire Council. He currently focuses on emerging technologies, safety trends, plastics aging, failure and forensic analysis, fire dynamics, and the evolving definition of safety. Tom joined UL in 2001 after a 21-year career at AT&T Bell Laboratories and 3 years at the Upjohn Company. He has 17 patents and certainly has made many, many presentations. We really appreciate your participation, Tom. So please proceed.
Thanks, Maggie. I appreciate it very much. Just want to double check that you're able to see my screen.
Yes, we can.
Great, thank you. Well, first of all, Maggie, I want to thank you, Pinfa, SAMPE, for this invitation to make this presentation today. And thank you for your endurance and patience throughout the afternoon. I also really want to commend all of the previous speakers. I hope it's evident to everybody watching this that it really takes an army of individuals to advance safety. It is a remarkably complex and intricate task, and it really takes the best of all of us to really advance safety. I would also say that my presentation, please understand that I'm a material scientist by training, and I have spent my 44 years in the chemical industry, and then Bell Labs, and then UL to really take on a topic, for example, and Maggie said emerging technologies, where I've become enormously fascinated by the hazards and risks and advantages of stored energy devices and batteries. You might ask the question as I get started, why UL? Why is UL so heavily involved? And certainly my colleague, Tom Fabian, has been enormously involved in this as well. So we're really taking a fundamental approach at UL. UL is composed of two organizations, really. There's Underwriters Laboratories, not-for-profit parent holding company, and then a for-profit subsidiary, UL LLC. The work that Tom and I have done over the years and others really focus in on fundamental aspects of safety. The work in batteries and transportation really went in earnest when UL supported the NTSB and the Boeing 787 investigation, where we had 21 experts involved, helping NTSB focus on probable cause and systemically, how did the system contribute towards this failure or lack of it. And so ever since then, we've been heavily involved in addressing this issue. So what I'd like to talk about today is frame the problem, understand from all of you who are interested in the drivers for advanced materials, drivers for innovation at the material science level to enhance safety, looking for opportunities. I will lay the groundwork for what we're doing and also where the industry is going. So I'll talk about very briefly lithium-ion technology, address the issues specifically related to aviation, and then the newly formed DOT PHMSA Federal Advisory Committee that I'm currently participating in. We'll move to the examination of the supply chain, look at the International Civil Aviation Organization initiatives to advance safety, and finally wrap things up. So let's take a second to really look at this technology. I mean, it is truly remarkable since 1985 with Stan Whittingham, Yoshino, and Goodenow really addressing the issues of lithium as a critical aspect of rechargeable battery technology. It's truly remarkable what's happened. And as you are all well aware, these three individuals did receive the Nobel Prize a couple of years ago for their massive contributions to changing the world. Also, what's important to realize, and what I call the arc of growth here, is the truly remarkable expansion from fairly primitive single cell, small device application to multiplicities of cells, as you should see in the curve from 2005, development of different formats of cylindrical, prismatic, and pouch technologies, and then the enormous applications that are both for consumer electronics, a myriad of home use, power tools, motive applications for scooters, electric vehicles, aircraft, more electrified aircraft, as you see in the 787 and the Airbus A350, as well as massive installations of batteries as it is today with stationary energy storage. All of this is solely made possible by battery technology at the cell level. So when you look at the various applications, you can see I've listed them here, but please understand that you really have to start from the cell. And in fact, what we have done at UL is conduct fundamental investigations into the failure mechanisms of these individual cells and looking at propagation. And so please keep in mind through all of this, we're talking about redox reactions an electrochemical phenomena where you have both the duality of both the electrical safety in terms of arcing and shock hazards, as well as the corresponding fire hazards of ignition, fire explosions, and deflagration. In some ways, we say it's sort of the worst of both worlds. You have both the electrical side and then the fire side. So in these incidents, I'm going to go through this fairly quickly since I have only a very short period of time. Please understand also that I provided Brianna and Maggie copies of my presentation for future reference. So I'm going to move quickly so that we can kind of get to the punchline. So basically incidents, what has driven this? There's a number of incidents that I'd like to list here that you're well aware of. These have made the headlines. There's nothing shocking about this other than the frequency and diversity of types of incidents. These consumer products have really driven the CPSC to issue a number of recalls, and I'll mention that in just a second. But it's important to understand that these are enormous headaches and challenges and threats to aviation, because all of us travel. We may not have traveled in the last 12 months, but we certainly have traveled previous to that and in the future. All of this equipment is taken onto aircraft as passenger belongings or in checked luggage. Larger format applications, as you see here, when you look at hoverboards, you look at the Chevy Volt test vehicles that ignited 2 weeks after side impact crash testing in a warehouse. I earlier mentioned 787. And you look at stationary fires that have occurred, Tesla fires, and if you want to see an exciting video, Google NASA robot battery fire. It's the guys went out to lunch and their lab almost burned down. I should also mention in the evolution over the last 30 years of battery technology, one shocking example, as you're well aware, South Korea is an enormous driver of this technology for manufacturing and applications. And in 2019, they had in excess of 20 major stationary energy storage fires. These are full up designs that caught fire, creating problems. The other thing that I'd like to mention in terms of this global scale of what you're looking at here is PERBA, the Portable Rechargeable Battery Association, has cited a statistic that the lithium in your cell phone or your power tools has typically traveled 24,000 miles from the ground of lithium in the earth through fabrications, modifications, integrations, and shipment to your pocket. So please keep that in mind, that this is a massive global scale. The transportation incidents and manufacturing incidents are listed here. Sad to say, we've hit the 10th anniversary of UPS Flight 6 crash in Dubai that killed the crew. And in fact, that C-shaped structure that you see there was an army barracks housing about 1,200 soldiers. And so they only came within a few hundred feet of demolishing that complex. So the tragedy could have been even worse. LG's factory in South Korea has had several fires, as well as other fires in other operations in China and so on. And then Asiana 747. As I mentioned earlier, you talk about CPSC, as you're well aware, the Consumer Product Safety Commission in the United States has direct jurisdiction around these kind of products. And they've issued, and I've taken it upon myself to study these recalls and so on, that they've had in excess of 150 recalls involving 21 million units of battery-related technology since 1990. The problem here, though, among other things, and these incidents were driven by small or large fires, injuries, sad to say, worse, deaths and property loss. The problem, though, is that generally the guidance that's given is, return suspect or identified devices to the manufacturer, not thinking that that's going to end up back on an aircraft. And I'll get to that in just a minute. So in aviation, one of the things that I wanted to point out, and again, please understand, I defer to my colleagues on previous presenters who are aviation, within the aviation industry. I'm a student of aviation. But one of the things we've examined in talking to the pilots and so on is that on a typical flight profile, non-battery related, the majority of incidents occur during takeoff and landing. So these are typically what we see. When it comes to batteries, however, please notice the lower chart where it is the time in flight where they see the greatest danger. And based on the Transport Canada and pilots all over the world are deeply aware of this statistic, is that once an incident is set in motion in aircraft, they only have 17 to 19 minutes until loss of control. And if you look at the various incidents that I've mentioned earlier, UPS 6 and Asiana and others, is that number really bears out. So this is of enormous concern to flight crews in aviation. So one of the things that has happened, and please understand the enormity of this in terms of the global scale of battery technology, is that the US Department of Transportation and PHMSA has been directed by the US Congress to establish a new advisory committee. And this advisory committee, of which I'm a member, I was named, was part of the FAA Reauthorization Act in 2018. In there, the committee was established under what's called the FACA, the Federal Advisory Committee Act, to select individuals with a certain requisite expertise to get together to examine all aspects of battery transportation safety. The official name for this is the Lithium Battery Aviation Safety Advisory Committee. The aim of this committee is to really carefully examine all aspects of this in terms of transportation of lithium batteries. Manufacturers in the different industries, air carriers, members of the federal government, and so on. The committee will also review methods to decrease risk posed by air shipment of undeclared lithium batteries. Our work is really directed towards directly making recommendations to members of the US Congress so that they can step back and advise the international organizations of the United Nations, IATA, and ICAO about changes. One of the things I think that is most important for all of you to recognize is, however, the burden of risk of safety lies with the air carrier, not the FAA, so on, and not the other United Nations and so on. It all comes down to the carrier. And one of the things that we're working on now is to say, are there industry developed initiatives that can take place developed by the industry for the industry to enhance safety? So in this representation of this PHMSA advisory committee, you can see a number of the logos and organizations that are involved. Besides UL, of course, we have Boeing, Apple, GM, Hawaiian Airlines as the one passenger carrier, UPS, we mentioned earlier about Medtronic, they're actually deeply involved in medical device transport and so on, Walmart. So please understand this is a very diverse organization, a group of individuals. In the subcommittees of this Federal Advisory Committee, we've divided ourselves into 4 different subcommittees. One involving data incidents that I'll talk about in a second. The second is the supply chain safety and integrity subcommittee, and I chair this committee. Regulations and gap analysis, and then hazard review. The structure of these subcommittees is actually quite logical because number one, if you can't logically talk about aviation incidents in very specific form in the first subcommittee, you really, you can't address the problem. So we've developed a very enhanced program, which I'll get to in a second, which talks about when, where, why, and how do these battery incidents happen. The second is in my area is with the team that we have, is to start with battery chemistry and technology from way back in design, raw materials, manufacturing, quality control, that leads to the shipment that ultimately ends up in cargo, or at least, or the device that ends up in the passenger's pocket or belongings. Next is the regulations. We're really looking here at how implementable are these regulations. And in fact, it's sad to say, but many of them are unrealistic when you look at state of charge. You know, are the major carriers really going to open shipments to validate that the state of charge is 30%? And the answer is no. And last is hazard review. We're going to be looking at the intrinsic reactivity of batteries during failure and how do we mitigate the risk. Mitigation of risk, please understand, has a lot to do with advanced materials development. So let's talk about incidents just for a second. TRIP is an acronym that stands for Thermal Runaway Incident Program. This was developed originally at United Airlines, and it went to American Airlines as a voluntary program, and then it moved to UL. The not-for-profit side of UL has invested tremendous amounts of money to move this forward, to make it as comprehensive, effective, and user-friendly as possible. And what we're now talking about doing is handing this back over to the US government so that they can literally move this forward in a more sophisticated way. We've seen a huge number of incidents and a variety of incidents. More to this will follow, but I want you to know TRIP is underway. In the supply chain, again, which I referred to a minute ago, we look at all aspects of battery technology supply chain to understand, can we obtain more information from the battery industry to enhance decisions that are made literally at the speed of commerce in terms of shipping batteries, or whether passenger airlines should accept or reject battery technology as passengers present. It could be mobility aids, it could be consumer electronics or whatever, but in fact, we see 2 separate ecosystems involved here: the dynamics of passenger airline battery safety and then cargo airline battery safety. Now, what I'd like to show you here is something to show you how complex this has become. In new shipments, and we're talking now massive cargo, and battery cargo, as you're probably well aware, is forbidden from passenger aircraft. So in many ways, what I'm referring to right here is massive cargo operations. So under new shipments, we're looking at cells, batteries as components or battery containing devices. However, in the 30-year arc that I just mentioned on my 3rd or 4th slide, I would say now that the technology is so mature that we're getting into what I call the many R's. Returns, repairs, reuse, repackaging, repurposing, recycling, or resource recovery. It just came to me one day that, you know, in dealing with retailers or so on, that reverse logistics is presenting an entirely new massive problem because can we invent new fire-resistant and economical packaging boxes that would mitigate some of the risk? You know, that old adage, you know, if it fits, it ships by the US Postal Service is quite a nemesis now, because in fact, a lot of batteries are being shipped reverse logistics, and the consumer or shipper is not declaring what it is. So undeclared shipments is a massive threat in airline safety. I apologize in advance for this slide, but I want to actually emphasize some very key points here when it comes to aviation battery assessment. I will give you the punchline though, and focus on the green areas, because you in the materials industry might particularly want to be aware of what I'm going to say in just a second. So to walk through, if you look at the whole left-hand column, in many ways, this represents the current state of battery transportation safety. Uncharacterized cells, counterfeit cells, unstable batteries. Well, I've said that twice. So, oh yeah, there's a reason for that. I'll get to that in a second. You can actually have, you know, well-characterized batteries that have been undergoing some kind of electrical or physical abuse that can make them unstable. So in fact, we do see different categories of unstable batteries. Improperly packaged, inadequate packaging, and you can go down the list. What we are trying to do in this Federal Advisory Committee through the supply chain and the other subcommittees I mentioned is what can we do to move the axis towards a safer state. It's not going to be any one activity. It's going to be a multiplicity of improvements that will lead us from the unknown to the known through testing and certification, validation and verification. Advanced materials, I believe, is an enormously exciting new prospect as it relates to both packaging and what I call protected freight. And what I mean by that is various fire-resistant materials as the containers that are used in what's called the unit load device that aggregates shipments into cargo freighters. For example, the 757, 767, 747, and Airbus. There is the fire-resistant endurance materials. But I would say packaging and fire containment covers and ULDs, extremely exciting area, as well as enclosures. So I should say towards, as I move to the end of this, is that even the International Civil Aviation Organization in Annex 6 is really putting a huge emphasis on cargo safety in terms of intrinsic hazards, the capabilities of the operators, and the other items on this page. The direction of this is towards greater oversight, greater focus on safety, greater clarity of what is in that cargo that the air carriers have to deal with. And I should add that this is universal to all modes of transportation. This is not simply an aviation issue. You know, heavy cargo shipping, rail, trucks, down to the van that delivers your product. All of these have undergone severe problems, fires, and incidents in transporting batteries. So in conclusion, this technology is enormously exciting. It's an essential part of our lives, and it's not about to stop. Batteries are going to get bigger. They're going to get more energy dense, and they're going to get more diverse, driven by the applications across everything up to stationary energy storage. Those devices have to be shipped internationally, and that battery technology represents one of the major hazards in terms of dangerous goods to flight operations. The technology is complex. However, we do believe that there are ways in which we can further characterize batteries in terms of testing to failure to quantify the hazard. Testing to failure is the single greatest opportunity towards determining what a what precautions you need. For example, I use the analogy quickly of what's called flashpoint is to liquids as testing of failure is to batteries. As soon as you know what it is, you know how to adequately handle and ship it. The new PHMSA DOT Federal Advisory Committee has a duration of from between 2 and 6 years, and we're really focused in on this ecosystem. We anticipate broad-based recommendations to Congress and that we are giving our interim updates about every 6 months to address this issue, and members of Congress are deeply concerned. Thank you very much, and I appreciate your attention and look forward to any questions.
Tom, thank you so much. As always, an excellent presentation. There was a question, but it's kind of disappeared. Was it answered? I wonder. The question really it was from Bob Young. It was about, would a, I guess you'd say, metal container, some type of container to protect the batteries with an inert gas, or would there be self-oxidizing? Is there any?
It's a really, I appreciate the question. I would say, you know, the answer always comes down to cost and weight. You know, the container is a problem for air carriers. You know, it adds weight and it doesn't add a lot of value. I would say lightweight, high endurance materials, ones that are cost effective, are absolutely the way to go. Metal containers are, you know, even aluminum melts at 900 degrees and I can burn a hole through it with a battery. So I would say, you know, there are some concerns. I would say advanced materials really are of great interest to all of us. And so I encourage innovation.
Tom, can I add a quick comment?
Absolutely.
The Department of Defense just actually conducted a competition for a battery container for Navy ships. And part of the requirements, lightweight, withstand the conditions. The atmosphere inside is not so much an issue because all of the energy is already inside the battery. Yeah. But what it truly is about controlling the heat release and the gases coming out of the batteries. So, and there are some lightweight solutions to that, which we're going to propose to PHMSA.
Yeah, Matt, thank you. I really appreciate your comment. And to add to what you just said, you know, the terrible tragedy out in California where about 24 divers died on a dive boat. The NTSB determined probable cause was charging of batteries. And I actually had Robert Sumwell text me and ask me if sort of a vault or some kind of enclosure could be developed, and because he knew I was a materials guy, and I said certainly yes. I said, you know, let's get the industry pointed in that direction. So Matt, you're exactly right.
Unfortunately, I came in second place in the competition, not first place, but we still made some money on it. But.
Yeah, well, but the answer is containment. Yeah, we're not going to improve batteries in our lifetime. We have to improve safety.
Absolutely.
Okay, so thank you. I would
Maggie, I was just going to say, we are obviously over time by a few minutes, but we can take a couple minutes just to close it out. Great presentation. So clearly we need a follow-up session on this.
That's the idea, Brianna.
Exactly.
Come back to us for another one.
Yep.
Well, so I would like to personally thank all the speakers. As I said earlier, before we started, they've been really good getting back to me, hanging in there, telling me, yeah, they do it if you know, everything worked out with timing availability. So I want to thank them all. They've all been great and they've been responsive, right, Brianna? They've gotten back to us and it's been
absolutely
excellent.
Yeah,
Tim,
thank you guys.
Would you like to make a comment?
Ditto. Thank you. Speakers were terrific. And also thank you to Brianna keeping this all together today. Thank you, Raj. And we look forward to some joint sessions in the future. This was terrific. It's cutting edge. It's important for fire safety, and let's keep on it.
Okay,
absolutely. So as we've said before, the session recording and slides will be handed out, so more to come. Thank you from SAMPE to all of our speakers, Maggie and Tim as well at Pinfa. Much more to come on this. We hope to continue this partnership with you guys for many years to come. There's obviously a lot of work to still be done in this area. So thank you guys, and thank you everyone for attending, and we'll be in touch soon.
All right, thank
Great.
you.
Bye everyone.
Bye.
Thank you.
Thank you.